Okay, so there is a crossflow shell tube heat exchanger made of steel. It has water flowing at 6 kilograms per second with an inlet temp of 283 Kelvin. If the process being cooled is ethylene flowing at 11 kilograms per second, what will be the exit temperature of the water in the ethylene when the ethylene inlet temp is 373 Kelvin? And you can see an example of this heat exchanger to your right, where it has the cold water on the outside and ethylene in the middle. Our heat exchanger has some preset geometries. The shell will be 2.5 meters long, and the shell will also be 0.5 meters in diameter. The shell inlet and outlet diameter is 0.1 meters, and the process inlet and outlet diameter will be 0.1 meters as well. So first what we're going to do is we will open up Ansys FLUENT. And after right-clicking the geometry and going down to the properties, we will see the properties on the right hand of the screen. And this problem will be in 3D, so you see we select the 3D option there. Now we'll right-click geometry again and select the new design. And we'll be starting this geometry in the XY plane. And you'll select circle and expand it out. The size isn't super important right now. You're going to assign dimensions afterwards, as you'll see me do here. And that is a 0.5 meters. Next, we will extrude the shape. You'll click the sketch and you'll apply that geometry and then change it to add frozen. We are at 2.5 meters. You can see here where the shape will be after the extrusion. And there's our shape. Next, we will need to make the process pipe that goes through it. So we'll go back to the XY plane. Similar process of making a circle first and then extruding the distance. And the same process again of selecting the sketch and assigning that as a geometry, add frozen. And then it remembers our 2.5 meters from before, so you can see it coming out and generate again. Next thing we're going to do is the inlet and outlet for the shell, which is on the top and bottom. So we move to the XZ plane. And once again, very simple. You make the circle, and then you're going to extrude the distance that you desire. And you can hide the previous made objects to make it easier to see. And for most dimensioning, you can leave it in the general setting. I accidentally over-constrained right there. But like I said, for most, you can leave them in the general settings. Sometimes you'll have to select the specific horizontal, vertical, radius, or diameters. You can see right now I have to select the horizontal to measure the distance between that axis and the edge of the inlet. And then once again, another extrude. Always make sure you do the add frozen if you're going to have an object with a fluid flowing through it. And I changed my angle here to see which direction the extrusion was going to apply. And I went back to make sure it came fully out of the shell. Now I'm going to repeat this process in the ZX plane again for the once again, this project is purposely simple to give a explanation to someone who might be new to Ansys. You can also go into a lot more detail with these drawings. But for our purposes here, we try to keep these measurements simple to make the calculations easier. And that was a calculated value I had to make sure the inlet and outlets were the same distance from the edge of the shell. You see here they're going in the same direction, and we want it to go downwards, so we can switch that normal to reversed. And there we have it. Now we'll show all the bodies again. And there's our basic shape for our shell and tube heat exchanger. Next, we want to create a boolean in order to subtract the parts of the inlet outlet that pass through the exterior of the shell. We want those parts to stop right at the edge of the shell, so they're just connected. So you'll select your tool bodies, which right here I made a mistake and got them flipped backwards. So you'll see here it doesn't do what I want it to do. So now I could go back and I could right click my boolean. And edit my selections, and I'll flip it to where my target bodies are the two inlet and outlets. You can hold control and click both of them. And then for my tool body, I'll select the shell. And always make sure to keep the preserved tool bodies if you want them to stay there. If not, the inlets outlets would be, or the shell in this situation would disappear. Now I'm going to create another boolean to eliminate the part of the shell that the pipe is going through, so that area is occupied just by the piping. And you'll see here I forget to change the preserved tool bodies to yes. And it cuts out the shell, but it also cuts out the pipe in the middle. So, easy repair. And this last thing is one more boolean, but I'll change it to unite to make the shell and the two inlets all one part. Hit generate again, and you'll see my parts went from 4 down to 2. So one part's the pipe, and the other part is the shell and the two inlets. Now I want to select both of them by using Control and form a new part. Now I'll go back to my workbench, I'll right click my mesh, and click Edit. I also cut out the loading time for these pages. It may take a little longer, just for the benefit of the video. I'll cut those parts out. Now I'm going to name all of these inlets and outlets, these bodies. So here I have the hot outlet, and the cold inlet. And make sure you have the right selection tool when doing processes like these. So right now I have the face selection tool. You can see it in those green cubes at the top of the screen. You can see all my name selections there. When you click them, it will put an arrow near it so you know where it is. Next, I'm going to do another face selection, and I'll select the entire outside of the shell. And I will aim at the adiabatic wall. And now if I hide the shell, the pipe will be exposed. And I can do the same process with it. These names become important when you get to the setup functions. So it's always good to overname everything. Now I'll get the body selection tool, and I will name the domains, which is where the cold water and the hot ethylene will go. So this will be my hot domain. You need to do this to assign material properties in the next steps. Okay, now that all of my parts are named, I will show all my bodies again. And the next step is going to be starting the meshing. So I'll start by assigning sizing. I'll do edge sizing and select these two edges. Like I said before, we're doing this very simply. You can go way more in depth with meshing like you can everything else. This 70 is what I got from trial and error, figuring out which setting makes the mesh look the best. With the student software of Ansys, there is limitations on meshing. With practice and repetition, you can almost eyeball how well the mesh is. You really want it as dense as possible to get the best results, but if you get it too dense, it causes unneeded calculation times. So here my mesh, it's okay. I'm not satisfied with it. So here I can hide the other body and zoom in to how it meshed the inner pipe. And a tool you can use if it's not quite as dense as you'd like it is a refinement tool. And then I'll select that face and apply that as a geometry. And it won't let you partial numbers, so it has to be either 1 or 2 or whole numbers. This is another situation where I skip past the loading. That usually takes some time on your computer, so you're just going to be patient with it. Now you can see my meshing is much more dense, and it will have a much more reliable answer. Once again, depending on your geometry and what your outcome you desire, your meshing strategy may be different. But for my situation, the meshing is now complete. So I will go back to my workbench and start to edit the setup functions. I always like to use double precision, and for solver processes, once again, it's for this project that works best. This also takes a while to open, but I'm going to edit out some of that loading time, so it may appear faster here. And we'll start, since we're working with heat and we're trying to find temperatures, you want to have the energy equation on. Next, we'll set some flow parameters. These are settings that I've found to work best for this type of problem. And you can see there's a lot more settings we can change here. Ansys could be as simple or as complicated as you'd like. Next, we have to load in the materials. So right click new, and then we'll go down to water, which is going to be our cooling. We'll hit copy. Then we close that, and then click create and change. And now we need to do the same process for the ethylene. And there's tons of chemicals on here with all their assigned properties already. You can also edit them if you'd like. And now we have it. We have our ethylene and our water. And air is an aluminum. Is a default setting that Ansys uses. And we want to enter our steel for our shell body. And solids is an identical process as fluids. Okay, now we're done with materials. Next is our cell zone conditions. This will be our hot and cold domain. This is where we apply those materials to our hot and cold areas. So here's our cold domain, which we're using water. So we'll click the drop down and select our water. And then perform the same task for the hot domain with the ethylene. And up next is going to be our boundary conditions. These are all those name selections we did earlier. So our cold inlet, we're going to change this type to a mass flow inlet. Depending on your problem statement, you can select different types to assign the properties. And if you ever notice that the thermal option isn't available, you most likely forgot to turn on your energy equation in the beginning. So you can always go back and change that, and then the thermal properties will be available. I did make a mistake here for the direction specification method. I should have put normal to the boundary, and I just forgot. You'll see me go back and change it after these few steps. So if you're wondering later on why I go back, that's going to be why. And here I'm doing it now. For our outlets, those are the areas where we're looking for data. So we're not going to assign any data to it. We're just going to make them outflows. Then our walls, we have to start assigning thicknesses to these walls. and then also material. Which all these settings will be specific to your problem statement. Once again, just trying to show the process you go through to calculate a problem with Ansys. Okay, and that is all of our boundary conditions. Next, we're going to move on to setting the residual monitors. This is another setting that Ansys usually defaults. Then also, before we can run our calculations, you'll see here I start to assign the number of iterations. And as it says there, I forgot to initialize, which is a couple steps above that. And usually for simple problems, you can use a hybrid initialization. For my case, for whatever reason, it didn't want to do it. It didn't converge. So I had to switch to standard, which is a more specific version of the initialization. Okay. And now it's initialized. I click calculate, and this takes quite a bit of time, depending on the iterations, depending on your processes, and also depending on your computer. Let it run for a little bit just so you can see how it's going to start out, and then I'm going to edit out most of the in-between time, and then show you the final results. And then this screen will come up, this calculation is complete. And then you can go to your reports and use surface integrals. And when you open that up, you click the drop down and do mass weighted averages, and then select your temperature, and then select the zones you want to find them at or display at. And then there we have it. You see our cold inlet and outlet temperatures along with our hot inlet and outlet. You can see it only cooled the liquid, not even a full degree. So this is not a very effective heat exchanger. It did heat up the cold water quite a bit. So if we were the design engineers, we would want to go back and redesign this heat exchanger to make the ethylene cool better. But for now, this was our video on how to use a basic function in Ansys FLUENT to calculate the outlet temperatures of a simple heat exchanger. Thank you.